Hello everybody. Charges and the electric field, that's today's topic. I have drawn here an example. So we have a positive charge in the middle, which produces a point symmetrical electric field. For instance, at this position we will have an electric field pointing to the right, having a certain strength. So if you encounter an electric field, it's always a charge being the reason for this field. And we will have a more theoretical look at this issue in this lesson. Let's begin with a definition. What is the so-called surface charge density, or just the charge density? The name actually just tells you it is the density of the charges on a given surface. If you have an area given, you might have a certain amount of charges on it. And the charge per area is given as the charge density. The symbol for it is the Greek small letter sigma. So you might know the capital letter sigma, surely. So here it is the small sigma. And it is defined as the charge per area. The unit, therefore, coulombs per square meters. Let's do an example. So you have a big metal plate 1 by 1 meter and you put on it a charge of 3 microcoulomb. What's the charge density on this surface? Give it a try. Basically, it is quite simple. Chances are that you have gotten 3 times 10 to the power of minus 6 coulomb per square meter. So be careful. If you have a metal plate, it has 2 surfaces on top and at the reverse side. So the area of it is 2 square meters. You have a small rim, of course, so we can neglect that. And therefore, the result here is 1.5 times 10 to the power of minus 6 coulomb per square meter. Let's do a second example. Here we have a sphere that is charged with 3 microcoulombs. It's also given the radius 1 meter. Give it a try. So here we can just go straight forward. All we have to know is the area of a sphere, which is 4 pi times r squared. And if we put in the numbers, we get 2.4 times 10 to the power of negative 7 coulomb per square meter. We go one step further now. See what is the impact of such a surface charge density. So let's assume we have a metal plate that has charges on it. So I take some positive charges being on this metal plate. So we will have electric field pointing away from these positive charges. The electric field will look something like that. So it is the charges that are causing this electric field. And it is quite clear the field will be the stronger the more charges we have. So we can just say that the electric field has to be proportional to our sigma. The definition was made just like that, but they had to choose for some constants, and therefore the electric field is given as sigma divided by the epsilon 0 that we have encountered in Coulomb's law already. Epsilon 0, or the permittivity, is given as, same as in Coulomb's law, 8.854 times 10 to the power of minus 12 Coulomb squared per Newton meter squared. We can some sort of check that using Coulomb's law. Let's do that. We take a sphere. This is our source with the charge Q1 having a radius given here as R1. And just a little bit away from the surface we have here a test charge. We call that Q2. This test charge is experiencing a force, which will be in this direction. Or we could also say there is an electric field pointing in this direction. So we can do two approaches. We can calculate what is the force using the direct approach with the Coulomb's law. Or we can go for the approach using the electric field. So let's write down Coulomb's law. K times Q1 times Q2 over R squared. Or we can use the approach with the electric field, where the force is given as Q times E. The electric field E is produced by the charge Q1, so the Q here, the test charge, is Q2. Well, if you calculate the force using Coulomb's law directly, or if you first calculate the electric field and then the force, should not make any difference. Therefore, these two sides have to be the same. And therefore we can write here, instead of the K, I'm going to use 1 over 4 pi epsilon 0. So you remember that was this second version of Coulomb's law, times Q1 times Q2 over R squared. And this has to be the same as Q2 times the electric field E. Q drops, and we can resolve for the electric field E. So we are left with Q1 over 4 pi epsilon 0 R squared. Let's go back and see what was the R. So the R is the distance in between the two charges, and if we are just above the surface, then this R is equal to r1 the radius of this source sphere. So we can put this in here to be r1, and we can now have a look and think about what is 4 pi r squared on a surface. This is just the area of a surface, and therefore this is q1 over the area. We could also say 1 times 1 over epsilon 0, and q over a is the surface density. So we have shown that this is sigma over epsilon 0, which was just the law to be shown. Let's apply this to a parallel plate capacitor and calculate the field in between the two plates. So as a repetition, parallel plate capacitor was two metal plates parallel to each other with a certain spacing. So we have here the top plate. I draw it in red since it is supposed to be charged positively, and I draw the lower plate, which is charged negatively. In almost all cases, the two plates are charged equally, so the magnitudes of the positive and the negative charge is the same. Now, the red plate will cause an electric field pointing away, and if we are just interested in the part in between these two plates, it will just look down, while the negative plate will have a field pointing towards the plate, so it will be pointing downward as well. What is the electric field of the top plate? Well, it is sigma over epsilon 0. Sigma is charge over area. We have to be careful, the charges is on both sides of the plate, so it is just 1/2 of the charge divided by the area times E0. Same thing for the blue plate. We then can add these two electric fields because they're pointing both to the same direction. And we get the total electric field given as Q over A times epsilon 0. Note that Q is the charge that one of these plates has. The other one will be always charged with the same magnitude but opposite sign.